we can start with our second talk of this morning session. Our speaker is Michela Procesi. Michela Procesi, who will talk us about linearization in infinite-dimensional dynamical system. Okay, as usual, just raise your hand, both in presence or virtually, for any question. So we can start. So please, Michela.
Thank you. So I'm really happy to be here, especially in person. We can look each other in the eyes. And il puntatore. So let me see if I. So this is. Così non succede granché.
Puoi girare slide?
Posso pigiare, non è che. Posso mettermi lì e pigiare se mi piace.
No, che... C'è un cambio di slide anche qui? Sì.
Andato?
Sì. Sì, è spaventato.
Sì. Okay, so now we're set. So what I'm going to talk about is the problem in formal versus analytic linearization in dynamical systems in infinite dimension. But what I'm going to talk about is really PDEs. And I will go with rather simple examples. So let me, sorry, this is joint work with Laurent Stalovich. So what is the question? Let me see. Very naive point of view. So I take a dynamical system and I want to consider a dynamical system which has a fixed point at 0. And at this point, I'm really just writing the u dot equals some linear operator applied to u plus some non-linear term without making any specification. And if I write it like this would be finite dimension, infinite dimension, and the extremely basic question that I am thinking is what happens when I apply a group of changes of variables. So I take this dynamical system and I conjugate. And well, have to be a little bit more specific, of course, but the basic question is, can I conjugate to a particularly favorable form, which I will call the normal form, in, say, maybe this is, sorry, my change of variable psi, and it could be that with this change of variable, I reach an integrable system, possibly even explicitly integrable by quantities. And of course, I do not expect this to be true in general because equations are not generally integrable, but it's a question that you can ask. And actually, people asked this question at the end of the 19th century in the context of finite dimensional dynamical systems. So it's a good question. And the answer, well, the answer is it depends. And I have to specify. So I said at the beginning that I was going to consider Hamiltonian systems. But if you give up with that, it could be a complex equation, it could be real, and everything changes in the changing of this context. And also, as you can imagine, since what I'm looking at is a neighborhood of 0 at the end, because this is how I'm going to use the fact that I have a fixed point, then a lot of things shall depend on the nature of this operator L, which is linear, but is it semi-simple? So is it diagonal? And if you're in infinite dimension, of course, there is a number of other questions that you want to ask. Self-adjoint, I will typically ask that it's anti-self-adjoint. So there's a number of questions, but another important thing is what kind of regularity has the map with which I conjugate the system. So to keep close to 0, I will always assume that this map is close to the identity. So it will be the identity plus some nonlinear terms. So it has, and I will be interested in some neighborhood of 0. But if you recall all analytic mechanics, there are cases in which if you're looking for a change of variable, which is just continuous with continuous inverse, you have many theorems more with respect to the ones that you have if you ask even a little bit of regularity for your change of variable. So here, okay, I think I said this before, but let me restate it. I will consider Hamiltonian system. I will assume that if you ignore the nonlinearity, I have an elliptic fixed point, which means that I will have imaginary eigenvalues. And let me state it because of the previous talk. If I am in infinite dimension, I will be interested in operators which have pure points vector, because otherwise I can do essentially nothing. And this problem is completely different in its nature. And then this is an important thing, which is very natural in finite dimension, but in infinite dimension, it's much more weighty to ask. I will ask that the nonlinearity is an analytic function, which means that I will fix some phase space in the infinite dimensional context, some space of regularity, and I will ask that the nonlinearity maps the phase in itself in a regular way. And if you think about the PDE context, this means I cannot accept derivatives in the nonlinearity, which is a shame, but it's true. Okay, and then what is the context if I ask that n is an analytic function? Well, you could look at many questions, but for me, the two main questions are, okay, either ask that phi is analytic, so exactly the same regularity as the nonlinearity, or completely dual point of view, just ask that the phi is a formal power series. So by formal power series, I mean something that can be expressed as a formal sum of higher and higher degree terms. So it has a formal Taylor expansion, but not necessarily has any radius of convergence. Okay. And so what is the thing that I'm going to concentrate is the interplay between the formal results and the analytic results. And I will try to motivate this. I don't know when the slide comes, but I'll try to explain why this is an interesting problem. And I said linearizability. So what I'm going to do in this is still a very wide subject. So I'm going to look more specifically at questions. Can I find a change of variable that takes my nonlinear system and maps it exactly to its part? Of course, you don't expect this to be true for any question. So it's a very specific question at this point. But it's classical. It was studied, they all studied this question in the finite dimensional context. And if you don't have small divisors, you have this very nice result, which says that if you are formally linearizable, then you're also analytically linearizable. Okay? It's a very specific question. It's a very strong constraint to be formally linearizable. This is what these things say. Okay. And then if you are instead in a context where small divisors appear, which I think is the most interesting context, and it will be the one that surely you find yourself in if you have an elliptic fixed point at 0, then things are much more complicated. It's not necessarily true that formal linearizability implies analytic, but if you impose some conditions, which I will state later, I will talk about them a lot, on the eigenvalues of the linear part, then classical results, which were the beginning of KM theory for finite dimensional systems, say that formal linearizability implies analytic linearizability again. So what is the purpose is take a PDE or possibly classes of PDEs and see what, if any, of these mechanisms works in finite dimension. And I guess you know that there's a lot of results on Birkhoff normal form for PDEs, but this question here of the linearizability is more delicate. So I thought it was interesting. So the model I'm going to consider is the simplest one on which I'm able to work, because it's hard enough technically, even in this case. I'm not going to show the technical parts, but I assure you, technically it's heavy. It's easy to say the whole story, but technically it's not that easy. So I'm going to consider a nonlinear Schrodinger equation. And what you have to keep in mind is that I am working on a compact domain. So on the simplest one that I can think about, on a circle. And then I have, che succede? Ho fatto qualcosa. I pressed something that I shouldn't have. So my linear Schrodinger equation usual, what you should concentrate on is that I'm adding this term, which is a convolution potential, mainly because I want to keep things simple. I could remove this piece for many of the results that I'm going to say, but it simplifies things. So this just acts, so if you write your solution in the Fourier basis, it acts as a diagonal multiplication by Vj. And you can add, so here I put Vj in L infinity, but you could put it in L2 or make stronger requests on this decay of the Vjs. It's essentially irrelevant for what I'm going to talk about. And then you see the non-linearity. Again, I put the simplest possible one that fit my hypothesis. So f is a real analytic function defined in a neighborhood of 0, which is 0 at 0. So take f of y, then you get the cubic NLS, 3y squared, the quintic NLS, and so forth. But I don't really need it to be a polynomial for anything of this to work. And it's a Hamiltonian system. And at this point, I'm always going to work on the Fourier side because I like that. There I have a very nice comparison with the finite dimensional case. And so if you pass to the Fourier variables, you get this quadratic term, which is a chain of harmonic oscillators, each with frequency j squared plus Vj. And then I have my nonlinear perturbation in the Hamiltonian. And if you compute the Hamiltonian vector field like this is an analytic function on any well-behaved phase space, provided, say, that you take the phase space to be H1, and everything will work. So this is a nice context. And let me say, we can consider other equations. They have to be dispersive. I need here to have more derivative than in respect to time, because otherwise things become, maybe something would work for the wave equation, but I'm not sure. Things might be much more hard. And the other thing that I want is I really don't want derivatives in the nonlinearity. And this is a big constraint because, of course, I really would like to remove this. But this makes things much, much more difficult. So before going to why I want to do it for PDEs, let me just run you through what is the idea in finite dimension. And to run through the idea in finite dimension, just stick to take the NLS equation and just make a truncation instead of working in Z, take M modes. Of course, this is not an invariant subspace for the NLS. I'm not saying anything. I'm just trying to show you what happens. So what does Birkhoff normal form say? Says, so I'm calling these are the linear frequencies or just frequencies, omega j. And if they are rationally independent, all of them, weaker hypothesis might be given, but then fix any k, and you can find an analytic change of variable, which actually the generating function of this change of variable is a polynomial, and you have to keep that in mind because it will be important. And then this analytic change of variable maps your dynamical system in a piece in which you have the linear part, then you have a normal form piece which depends only on the linear actions or actions. And then you have a remainder. And the point is that this remainder has minimal degree 2k plus 3. So the bigger k, the higher minimal degree has R. Okay, minimal degree is just the minimal term in the Taylor expansion, of course. And so this infinite dimension is perfectly well known. It's called Birkhoff normal form. And the point is that it's well known also that it's not convergent, because if it were convergent, everything would be integrable, which is obviously senseless. So another thing that is well known, what's rather a nice proof, I think, is that this procedure converges at the level of formal power series. What does this mean? Well, it means that if you look at pk, and then you take the term, homogeneous term of degree d, then the limit as k goes to infinity of pkd converges. Actually, it is definitely constant. So it's a very strong convergence result in the formal power series level. And also another point which is interesting is that the formal diff of Knopf form is unique. This again is an important point. So you find that this is a formal power series, and then you send this equation into this, where this z depends only on the action and is fixed. Of course, it is not analytic in any ball around zero, but it's given as a formal power series. So ask a bit more, sorry. If you ask that the frequencies are Diophantine, which is a condition, I'm not going to think about it much, but it's a condition on linear combinations of the frequencies, a lower bound on these linear combinations. And if you ask this condition, which is satisfied by positive measure sets of frequencies, and so it's reasonable, then you have two results. One is a stability result, which says that if you start with a small initial datum, then not only the equation is well posed, which in this case is obvious, but you have that the solution stays inside a ball of radius 2 delta for times which are longer than any polynomial. So you see it's delta to the minus 2k minus 1 for any k. Okay, and then what you do with this result, you optimize k, and then you can use this to get exponential bounds on the stability. Actually, you can do a little bit more with some hypothesis on the nonlinearity, but this is what I'm going to concentrate on. And the other theorem, which is also very interesting, is what I said. If you know that it is formally linearizable, which means that z, the piece which depended on the action, is 0, then the change of variable is not just formal, it is analytic. These are the results that I want to consider. And if you think about it, this kind of results on stability, there are many results of this type for the MLS equation. While this thing here, it's more new, and I'll try to explain why. Let's see, just a reminder of the general setting, and then I will give you some motivation. So the general setting is this. I start with the nonlinear Schrodinger equation, which brings me to this Hamiltonian system, linear, quadratic, but linear in the vector field plus perturbation. And the things that I want is that I have a superlinear dispersion law, so more derivative in space than in time. Then I want to have at least one constant of motion, but actually the one that I really like is the momentum. So what does this mean for a PDE? It seems rather mysterious at the first, at least from that finite dimensional dynamical point of view, it means nothing particular. But here, it just means that F does not explicitly depend on X, on the space value. And well, it's a reasonable hypothesis that I can do, and I really need some condition of this type. Okay, this means that here, for instance, I could not accept, instead of a convolution potential, a multiplication potential. Once you have your Hamiltonian, your constant of motions, then the next condition, which was, I said, is the analyticity of the vector field. And actually, I need a little bit more, and this is slightly technical. You could ignore it, but it's important for the proofs. What I want is what is called the normal irregular or major irregular. It means this: you want to take, instead of taking the perturbation P, you expand it, you Taylor expand it. P is an analytic function, so you can do it, it's convergent. And then you look at the Cauchy major. So you put the absolute value of the Taylor coefficients. And then what I will ask is that I want the vector field of the majorant to be an analytic map from some ball in H1 to H1. Actually, I could ask HS with S bigger than 1/2. I need the dimension in an infinity to do this. Okay. This condition is a bit unpleasant because since it relies on writing the Taylor expansion of the non-linearity, this means that it depends on the set of variables that I am putting. I would like more intrinsic condition, but this is really, I have no idea how to avoid this. So it's important. And otherwise, I could change the dispersion law here. I could slightly change this constant of motions, but this I really need. And then the question is, can one perform the Birkhoff normal form? And by this, I mean exactly the finite dimensional one. I want to make a change of variable that takes my Hamiltonian and sends it to something in which this piece depends only on the action, and this piece is an analytic function with extremely high degree, 2k plus 1. This is 3. Okay, 2k plus 3 degree. And then the other question, which is not trivial, is if I am working in infinite dimension, do formal power series make sense? Of course, formal power series makes sense in infinite dimension. What I mean as a Poisson algebra. And that is not trivial. It's not true that if you take two formal power series and you make the Poisson bracket, the one given by this two form, then what you get is still a formal power series. You might get something that is infinity even at the level of formal power series. So this is a serious problem. And then once you have done these two, you can ask yourself the question, does the linearization theorem hold? And once you have these two, actually proving this is relatively fair. The most complicated questions are the first two. So, well, as you can expect, since I'm talking about it, the answer is positive. And the whole point is to fix a good Diophantine condition and to fix a correct scale of inverse spaces. So you remember that I was asking that the vector field mapped H1 in H1, but I will need much more regularity to get my results. And this would be a point which I think is interesting. So let's move forward. Remarks. So here, let me see what I can say. The question. So working with formal changes of variable is an extremely natural thing. People working in integrable PDEs have been doing it since the story of integrable PDEs began. And actually, what is true at the formal level and what is true instead at an analytic level is a really nice and natural question to ask. One of the things, so I was some years ago hearing a conference by Victor Katz on formal changes of variables around the integrable PDEs. And the point is that often when they look for formal changes of variables, they really use the PDE structure. So they look in the class of differential polynomials or differential formal power series, meaning formal power series in U, UX, UXX, and higher derivatives. Or maybe they might accept the x to the -1 applied to U, or so negative derivatives to U. And here instead, I am completely ignoring the PDE structure. So I'm looking at a much larger class of changes of variables, because the only thing that I'm asking is that when you pass to Fourier, and then you look at this change of variable in the Fourier space, this makes sense. Might not be expressed in these terms. And so this context is really natural, except that the Birkhoff normal form instead works much nicer in a much nicer way if I am close to a finite dimension example. And the other two things that I wanted to say, I mean, this seems a little bit anticlimactic, but of course you can produce equations which are linearizable and fit all my hypotheses. You start with a linear equation, you plug in a change of variables, and here you see I wrote v is equal to u, so close to identity, plus some cubic function of negative derivatives of u. Then you plug this in the equation, make all the computations, and you will get an equation that fits all my hypotheses and is, of course, both formally and analytically generalizable. And the problem is that I'm cheating, and I'm cheating too much. And I really don't know of examples where you are actually able to first prove that something is formally linearizable and then go to the analytic case. And the other thing, which is a slightly bit unpleasant, is that if I make rather more natural changes of variables, so let's say that I don't put negative derivatives, then of course what happens, and I wrote this equation explicitly because it was easier for me to do. What you get a nonlinear Schrodinger equation, but you see, of course, this has derivatives in the nonlinearity. There's nothing that we can do about it. And in this case, I'm not able to cover. What I could do in so what there are results on is on the case when v is equal to 0. So there are some results both on stability and on linearization. There are not results that you could do that. But really, for me, the big point is the derivatives in the nonlinearity. This is so what I'm saying that this question is admittedly much of an academic question. So it's very natural to wonder, you have to set up results in finite dimension, what happens in the infinite dimensional case. But I'm not really claiming that you can use it in any way. And also, since in finite dimension, it is the simplest context, of course, it's a good playground. And I guess at this point people have understood the big point is to go to cases in which you have derivatives, because there the result things are much less clear, and these ideas of formal result versus analytic result have been used in many contexts. So I have two examples. One is use the uniqueness of the Birkhoff-Normal form. Remember, I told you the formal Birkhoff-Normal form is unique in finite dimension. So to know this in the infinite dimensional context for a quasi-linear PDE is a big question. And the other point, which I'm going to discuss a little bit, is, as I said, in integrable PDEs. So say you have a PDE like the cubic nonlinear Schrodinger equation, KDB, in which you have a lax pair, or in which by some stroke of luck, you have infinitely many constants of motion. And then you would like to prove that in this case, you have convergence of the Birkhoff-Normal form. And these are very interesting questions of which there are many results, but still not a complete clarity. So let me see. First case.
This is true
for the cubic on the torus, you can find, well, you can do it by many indirect ways, which show that the Birkhoff-Normal form converges in a neighborhood of 0. But typically, the first proof was done by Kappeler, and he found the Birkhoff variables, and then from that, you can prove that the Birkhoff-Normal form converges. So, and that's actually the question that I've always asked myself. So let me first go through this, and then I will answer more fully. So, uniqueness of the Birkhoff-Normal form is important and has been used in many contexts for quasi-linear PDEs. So I have two examples in mind. One is this paper by Berti and Pusateri. There they considered the water wave equation, and it was well known, I guess in Sakharov, that the Birkhoff-Normal, the formal Birkhoff-Normal form up to order 4 of this equation was integrable. And the point is, what is there also an analytic change of variables in this? And there, the uniqueness of the Birkhoff normal form is used in a very subtle way. So it really helps. And another example I have in mind is a paper with Roberto Fala and Filippo, in which we considered another integrable equation, the Michela Procesi, and there again, we needed results from formal integrability to get the analytic results. So it's there, it would be really useful to have these things. And integrability versus convergence of the Birkhoff normal form, it's an enormous field. So let me just say that there's been lots of results in which you know that the equation is integrable in the sense that you have a Lax pair, and from that you construct Birkhoff variables. But the question of you just know the constant of motions, and from the constant of motion you want to deduce that the Birkhoff normal form has to converge, which is what you can do. It was done in finite dimension by Ito. That's a much more delicate question, and the paper which is closest to this is a paper by Daniel Bambuzi and Stalovic, who discuss exactly this question, but even if they could cover the NLS equation from there, it still is an indirect question. They cannot solve it in general. They have to put two strong hypotheses on the constant of motion for this to be really what one wants. So actually, of course, we started thinking about this problem. We realized that we weren't able to do it. We passed to linearization. And then what we hope is to gain from linearization some tools to understand the more general cases. It's been very instructive. So on the stability, I think maybe in this public, I really don't need to say this, but let me say it in case. There are a number of stability results for nonlinear Schrodinger equation. And typically they are on some scale of Banach spaces, say HS with large S. And, oh, sorry, ignore this sentence, I forgot to erase it. So what is the problem with respect to what I'm going to do? That typically, since they only want stability, they do all do some normal form, but this piece here, which you remember in my case has to depend only on the actions, well, they do not reach this the Z just depending on the actions, because so they reach the minimal normal form that will ensure stability. Of course, it's the wise thing to do. And also, this sentence is a bit presumptuous, but the Diophantine conditions are not really natural in my opinion. These results work, which I'm mentioning here. Some of them work on higher dimensional tori, but the Diophantine condition that they impose, in my view, are a bit sloppy. So we wanted a clean picture as close to as possible to finite dimension. So I said this, and the first point was to find the good Diophantine condition, and of course the second one was to find the good analytic context. But for me, the Diophantine condition is really beautiful, so I'll just look at it a little bit. So of course, I have to fix my space of frequencies, and this would be some little square for these VJs. So you see, it's very good for me to have a convolution potential, because I can just put a very simple condition of this type. And then what do I want? I want that if you take finite combinations of the frequencies, so you have some lower bound. So just look at this L. L is a list of integer numbers. But you have to see that the L1 norm of L is smaller than infinity of the de novo qualcosa. So what I'm trying to say is that in omega dot L, this is a finite combination of frequencies, except that it can be arbitrarily large, and can also the support can be arbitrarily far away. So, and what is the condition? The condition is you have this product, and this might look something not defined, because this is cannot be an infinite product, but in fact that's true. This condition here is just a finite number of terms, And if you were to restrict to a finite dimensional case, it really looks very much like a Diophantine condition. And it's extremely clean with respect to conditions on infinite dimensional cases. I don't know if you ever saw one, but typically they are rather messy, at least for me. And of course, the important thing is this has a large measure. So the Diophantine frequencies of this type are typical. So once you have this, se riesco ad andare, e non va avanti.
Inserisci, togli e diventi la pennetta. Sì, la penna era.
Questa?
Sì, sì, infatti, salta.
Però
Italia. Però non so a questo punto dove sono. Che è successo? Okay. So what is finally the result? Take Bourga's Diophantine condition, consider this equation or any equation in the class that I described. Then fix as a regularity space, Gevrey space regularity, of course, always on the Fourier coefficients of your solution. What does this mean? This means that my norm will be, I have, well, it's based on L2, and then I have a polynomial weight, J squared, and then I have this piece here, which is sub-exponential, e to the 2s square root of j, or I could have, so Japanese bracket is the usual, meaning the maximum between 1 and modulus of j. And I could actually have j to any power smaller than 1, positive. And of course, if you put s equal to 0, this is h1, and otherwise it's much more regular spaces. And then, voila, my result. Hopefully you can read it all. Assume that the frequencies are Diophantine. Sorry, I did not erase this. Fix s larger than 0. And this, sorry, here you could put some parameters. Just fix s larger than 0. Assume that your Hamiltonian vector field is normally analytic. Remember, it was the major end has to be bounded and analytic from h1 to h1. Then, for any natural k, you can find an analytic invertible symplectic map going from a ball, but here not in h1, but in gs, to a slightly larger ball in gs, which conjugates the Hamiltonian to the normal form, where now you see this set only depends on actions. You actually cancel everything out except the completely resonant terms, which only depend on the actions. And then, at this point, for this to be interesting, then the remainder is again normally analytic, meaning that the vector, the major end of the vector field is analytic from this ball in the space, exactly the same space as the change of variables. And it has, well, it keeps the attention. So, and it has minimal degree 2k plus 4. And if you wonder why before it was 2k plus 3, here it's just that it has to be dependent. Also, you have a very explicit bounds on Rk in this space. And well, let me say it, you can play this game in many other function spaces. This is just, I think, rather nice example. And okay, then let me go instead to the formal power series level. Well, formal power series means that you are going to consider a formal Hamiltonian, which is a sum with some appropriate coefficients of monomials, and the monomial is just the finite product of u's and u bars, u to the alpha, u bar to the beta. This is the usual complex notation for products. And the thing that I have to remember is that this alpha and beta, even if we are in infinite dimension, they have a finite support. So these are actually finite products. But if I don't say anything on these coefficients h alpha beta, this is just a formula. And then use the symplectic structure. And as I said before, this is not closed with respect to Poisson bracket. And here is where my constant of motion comes into play. And this was actually first noticed in a paper by Giuliano and Pasquali for the Dispersive equation. Again, slightly different context, but same idea. So I told you that I had the constant of motion, the momentum, which I forgot to put a J here, so it doesn't mass. I really want the momentum. And then I just restrict to formal Hamiltonian in which each monomial commutes with the momentum. And this is a well-defined space of formal functions. And then, sorry for the fancy sentence, F, which is the space of formal Hamiltonians with this condition, has a natural filtered Lie algebra structure. What does this mean? Well, it's closed by Poisson brackets. First thing, which is important, you can decompose it in homogeneous components, FD, which have a graded expansion with respect to the Poisson bracket. So if you take a homogeneous component of degree D1 and a homogeneous component of degree D2, their Poisson bracket is homogeneous of degree the sum. And if you're wondering if you're using Poisson brackets, you have -2. This is just because I scale the degree. If something is in FD, it means that as a polynomial, it is homogeneous of degree D+2, nothing particularly fancy. Then F is a complete direct sum of these homogeneous components. And other questions, other important point, you have the action of formal changes of variables. And it's just the exponent of the Poisson bracket of something of degree at least 1. So cannot prove any of this for you, but everything is true. So as I said, this first result was actually proved in this paper. The second one I commented. This third one for me was actually the hardest thing to prove. And in finite dimension, it's called the Baker-Campbell-Hausdorff formula. It's rather tough. And we really had to use it. This was the hardest part for me, at least. And then, okay, once you have this, if you have some experience in formal proofs, in the formal proofs in finite dimension, you see that you don't see the dimension anymore in any way. So if this is true and you have the Birkhoff normal form, then it has to work. And what you get is if omega is rationally independent, you take all Hamiltonians of the form quadratic piece plus a perturbation, which is at least cubic. And then you take the normal forms, meaning that they are the Hamiltonians, which depend only on the actions. And then you can always find a formal change of variable, which maps your equation, your Hamiltonian into a Hamiltonian, which depends only on the action, and the normal form is unique, exactly as in finite dimension, simply because you don't see the dimension. And then, if you know that also, so let's go at the linearization question, start with this equation, assume now that P is, the vector field is normally analytic, then, so the Cauchy majorant is analytic from H1 to H1, assume that omega is Diophantine, then you can, if you know that H is formally conjugated to its linear part, then in a sufficiently small ball, you can find a close to identity analytic symplectic change of variable from a ball in GS into GS, which maps the Hamiltonian into the linear part, okay? But you have to be careful that I really need this S to be positive. So I really need to look at the change of variables in higher regularity, because R, the radius in which this thing works, goes to 0 pretty badly as S goes to 0. So this really, I start from knowing that the map is analytic in a very large phase space, and then I deduce that the change of variable is analytic in a very much smaller phase space. But this is how things go. And so this I essentially already said, but let me say it again. The most interesting question is this, that you start from working in a larger phase space and you reduce to a smaller phase space. And the whole point is how small, so how regular must this GS be? And so what are the delicate points? The delicate points in which I'm using strongly the conservation of momentum is something like this. Suppose that you know that your Hamiltonian vector field maps H1 and H1. In general, there is no reason why it should map a space of larger regularity into itself, because it's true that this ball is contained in this ball, but this image is much smaller, so it's not a trivial question. And the conservation of momentum essentially tells me that this is true. And then another question, sorry if I did not introduce this too much, but the key of Birkhoff normal form is solving homological equations. And the point is that if you know that P maps H1 in H1, then when you solve this homological equation, you have to show that it actually maps GS in GS. And once you have these two things, which I am not saying that they're technically easy at all, but they are true, then everything works exactly as in the finite dimensional case. So if you're looking for the technical core, it's these two questions here. So, quanto tempo?
Altri 5 minuti.
Ok, così vado
Sì, sì.
avanti. So very fast, because this I don't think it's the most relevant point, but of course, once you have a Birkhoff normal form result, then you have stability. And the stability result that you get in Gillet class looks like this. So fix any positive S, assume that U0 in the norm S is smaller than delta, take an initial datum, so take the equation with this initial datum, and then you will stay in a ball for delta for time, which is sub-exponentially long. Okay? Exponent to logarithm of delta to a power slightly bigger than 1. So this is the kind of result that you get from the from Gillet class. Let me mention that you can do it also by other methods. For instance, Kamian actually did it for an NLS with one derivative and also got a slightly better exponent. So we never tried the optimality of the times because we were looking for closeness to finite dimensional context. And so what are the interesting questions? Interesting questions for me are these. There are probably many more. But so first, can we weaken the Diophant time condition? Second, can we deal with quasi-linear PDEs? This is the star of my questions for me. Can you work with PDEs in higher dimensional setting? I did everything on the circle. Can I do it in higher dimension? Can I do it in more complicated manifolds? Can I ignore the momentum conservation condition? It would be really nice to just put multiplication potential. I mean, I don't really care about translation invariance of this piece, but the convolution potential is not particularly nice for me. And other question, which I feel is really important, is can I lower the regularity? Okay, for me, these are the important questions. And of course, you can look at what happens for the stability case, which has been studied. So here is a little bit of literature. And in this literature, well, these equations here are on tori. These results here are on tori of any dimension. So the question of getting higher dimension should be favorably solved. These are on the wave equation with derivatives in the non-linearity. And actually, these work not only on tori, but also on spheres and solid manifolds. So again, hope for getting higher dimension. And these, which I think I commented on a bit, but maybe I'll concentrate a bit on this. These discuss Birkhoff normal form for PDEs with non-linearities in the derivative. So a good question is, can you put these two pieces together? So let's assume that you take a nonlinear Schrodinger equation with derivatives in the nonlinearity, and then you do the procedure by Roberto and Felice, and you make a technique to reduce the derivatives in the nonlinearities. Then can you put an algorithm like the one that I explained, and put these two things together and get exactly the same results that I discussed in a quasi-linear setting? Maybe it's wishful thinking, but I really would like to work, and I'm looking at Felicia because I want to ask him this question at the end. So let's rapidly run to the questions. Can we weaken the Diophantine condition? Yes. In finite dimension, you can do Bruno conditions, and here you can envision some weaker Diophantine condition. I'm not sure that that's very exciting, but you can. Can we deal with quasi-linear PDEs? Well, I said it. I think there are some starting point, but that's clearly a very tough question, but would like to understand it a lot. Third question, can I work on higher dimensional tori? Well, the problem is that, you know, the results that I mentioned, it's always the Birkhoff normal form does not just depend on the action. I think that's, again, a tough question, but one should be taken in consideration. On the fourth question, alas, I have essentially no idea. You can weaken it in some way, but it's very tough going, and I don't know what. And the last one, instead, the answer is again yes. Can I work in lower regularity? And let me rapidly show you, and then I'll say goodbye. But yes, but you cannot go to finite regularity. So if you want to work in HN with this n fixed, then you will get stability times of type delta to the minus n. You cannot hope to fix the phase space and make as many steps of different normal forms. And it's not completely clear to me whether this is unavoidable or if we're doing something wrong. I think this is a good question, by the way. And before I say goodbye, let me show you an example of lower regularity. This was suggested to me by Zara Hani. So he said, well, okay, take your usual piece that gives you that you're in H1, and then put the exponent, and instead of j to the 1/2, we put the logarithm of, well, something which never cancels, logarithm of j to the square, or to the cube, or whatever. And provided that this exponent is larger than 1, can you give results? And for the stability, the answer is yes. And you get this kind of stability here, which is rather ugly. But I have been told that there have been some results. I don't remember the name because I could not find the paper. But I have been told that there are results in which they consider exactly this regularity, and they get better estimates. They just get one logarithm, so it's to some power smaller than 1. So this seems a promising questions, and one which one can do. So, well, it was just thanks, so I guess I will go. No, è bloccato. Well, I'll say thank you.
So thank you, Michela, for the very nice talk. So it's time for some questions. There's some questions here in the room. Also check online. I can start with a quick question. And you mentioned in the case of higher dimensions. Okay, one of the problems is the fact that the Diophantine condition becomes more involved. But this is the main, what is the main difficulties to higher dimension?
So, well, of course, in higher dimension, you have the problem of multiplicity of eigenvalues of the rotation. So the first thing is that you cannot expect to remove pieces, everything except the actions. You have to reduce to removing. So if you have two Fourier modes on the same spheres of it, which have the same modulus of J, you cannot cancel them. But that's not a problem for stability. But of course, if you're trying to do this very strong result with linearizability, I think that would be also a serious problem, because that's not something that you can remove by Diophantine condition. That's a fact. You could try to use more constant. So the trick there usually is to use more constants of motion, because constants of motion reduce the multiplicity, because you can look at things, not only the eigenvalues of the Laplacian, but other higher Casimir functions for instance, the momenta. And that also is should be a good trick, but I think it's a rather tough question. What is nice is that all the properties, so immersion and homological equation, those things I think are still true. Is just you need just one constant of motion, and
Okay, thanks. Question for Vladimir?
Very small questions. The first one is connected with the following. Is it possible to study half-wave equation instead of Laplacian, take square root of minus Laplacian? And the second question to optimize this movement. Suppose in the nonlinearity, in front of nonlinearity, you put kind of projection that reduces everything to the resonant set, the bad guy,
yeah,
where scalar product is zero. And is there some result, kind of lower bound of t, kind of lower?
yes. Both questions. So half wave, no, I'm not able, because it might be that you can do something, but you need some better ideas. I really need a superlinear dispersion law, because otherwise my Diophantine condition is I am asking too little. I am not able to solve the homological equation. And so half wave, maybe, but you have to completely change the technique. I think that is interesting, and I know that there are some results on stability for the wave. So if they work from the wave, they should work from the half wave by Kong. There's a big similar like, but it's I think that's an extremely interesting point. And as for lower bounds, yes, there are. So there are the results. There are various results, but typically they are on T2. So because there the resonant part has this very nice and integral structure, and there they have lower bounds. So there are the ones by the I-team, which construct a solution which goes to infinity. But you might say, okay, but that is in the completely resonant case, v equal to 0. But as Marcel Guardia discussed exactly this question in this equation here with the cubic LMS. So you can do it, except that as far as I understand, these bounds do not really match. They are much longer. So you know that eventually things become unstable, but the timescale are still very separated. So I actually think that this should be studied a lot, because what they wanted to do is to construct something in which the Sobolev norm went to infinity or to arbitrarily, but to contradict this, you just need to double it. So I don't know if they ever made the computation with the precise intent of doubling. But,
online question. Okay, if there are another question, we can text Michela again.